Hello and welcome to my channel. In this video, we are going to prove that a particular set A along with the operation dot is an abelian group, right? And the set is defined as mentioned on the top right corner. So A is a set which contains all rational numbers, right? All rational numbers A of the form P by Q, where P and Q are integers, but Q is not equal to 0, and A is not equal to 1, right? So the rational number is not equal to -1. And A dot B, the operation is defined as A plus B plus A times B. So these are all rational multiplications and additions. Okay, now in order to prove that this is an abelian group, first of all we'll prove that this is a group. So the conditions, so the properties that we are going to show are closure and associativity, the existence of an identity element, the existence of inverse element for each and every element, and that would conclude the proof of this A comma dot being a group. However, we need to go a step further and we should prove that this group actually is indeed an abelian group by showing commutativity, right? Okay, so without much ado, let's dive into this problem and try to solve it. So the first property that we want to prove is the closure property. So let A and B belong to capital A, right? And since A and B belong to capital A, they satisfy being rational and not being equal to -1. So, um, so let us assume that A is equal to P by Q and B is equal to X by Y, and the conditions are as follows. The conditions are P and Q and X and Y are integers, and the denominators in these rationals, Q and Y, are non-zero because we do not know how to divide a particular number by 0 yet. Okay, so that's a different story altogether. Okay, now A is not equal to -1, and that would mean that P upon Q is not equal to -1, and that means that P is not equal to -Q. Okay, that's great. Now, B is also not equal to -1, right? Because that's the property of B being in the set A. So X upon Y is not equal to -1, and that would mean X is not equal to -Y, right? Okay, so these two equations, we'll be using them soon, right? In order to prove closure or associativity, identity, inverse, commutativity. Let's see. These two look very important. Okay, now let's try to write down what happens to the element A plus B plus AB, correct? Well, we do have the rational descriptions of these particular numbers, A and B, and maybe, it's the best to write them down here. So P upon Q plus X upon Y plus P upon Q multiplied by X upon Y, right? Okay, now as you can see that we can take the LCM as QY, and the first term will become PY, the second term will be QX, and the third term will be PX, right? Okay, now since P and Y are integers, right? Since P and Y are integers, this this fact shows implies that Py is an integer. And why are we doing this? Because we want to show that the numerator is an integer. So Qx are integers. It shows that Qx is an integer, right? There is another term in the numerator, that is Px, right? So P and X both are integers, right? And this shows that Px is an integer. And since these three are integers, and if we add three integers, we get another integer. So Py plus Qx plus Px is also an integer, right? So we have got an integer in the numerator. All right. Now, as you can see that in the denominator, we have got qx, right? We have got a qx in the denominator. So q and x are integers, and the product of two integers is always an integer. So qx, I beg your pardon, it's not qx, it is qy, right? So q and y are integers, which means that qy is an integer. And also, since q is not equal to 0 and y is not equal to 0, that implies that qy is not equal to 0. And all of these three facts, right, combine to give us that py plus qx plus px divided by qy is rational, right? So this is the first condition of any element in set A. Now the second condition is that this rational should not be equal to -1. Let's see now whether it is true or false, right? Okay, now in order to show that this particular rational is not equal to -1, look at the numerator. So in the numerator, we have got various elements p and q and x and y. And remember that we had p to be not equal to -q and x as not equal to -y, right? So let us try to substitute the values, these not unequal values, in the numerator and see what we can get. So this rational number py plus qx, py plus qx plus px divided by qy is not equal to, substitute p by -q. So it's -q times y plus q times, instead of x, let's substitute it by -y plus, instead of p, let's substitute -q, and instead of x, let's substitute -y. Okay, now we divide this by the denominator. Let's leave the denominator as it is, so qy. And this in turn is equal, now in this case it's equal, this is equal to -qy, and then minus qy, right? And then plus -q times -y is qy, so this is qy divided by qy. And then as you can see that the numerator, there is just one element left in the numerator, so that is -qy, and in the denominator we have got qy, and this in turn is equal to -1. So owing to the -1, owing to the unequal symbol over here, what we can say is that a plus b plus ab, which is basically equal to py plus qx plus px divided by qy, is not equal to -1. And since a plus b plus ab, which is a rational number and not equal to -1, therefore we can say that a plus b plus ab belongs to A, and that shows that A is closed. Okay, I can understand that this might be a little overwhelming, but this is an amazing proof of what we have here. All right, now let's try to prove that this particular operation is associative. Okay, great. So let's assume that A and B and C belong to capital A, right? What is the set capital A? The set capital A contains all rationals which are not equal to -1. Okay, cool. So let's find out A dot B dot C, right? Okay, so A dot B is A plus B plus AB, right? Okay, now that is operated along with C, right? Okay, so this would give us A plus B plus AB, right? Plus C plus, okay, so this is one number, right? So plus a plus b plus ab multiplied by c, correct? So this will in turn give us a plus b plus ab plus C plus AC plus BC plus ABC. And if we write this down in a better way, A plus B plus C plus AB plus BC plus AC, we can write that as CA, and that would be plus ABC. Okay, so this is one operation. The order of the operation is that first we conduct the operation A dot B, and then we conduct the operation dot C. Now let's reverse the order in the sense that first we would do B dot C, and then we do A dot with that one, right? So this is A dot. B dot C would be B plus C plus BC, correct? And that and then this entire thing would look as follows. So A plus, now we have got B plus C plus BC to be an element of capital A because A is closed, right? So this would be A plus B plus C plus BC, and then plus A multiplied by the second element, that is B plus C plus BC, right? Okay, now let's see whether we can simplify this and get the result that we have seen above. So this is A plus B plus C plus BC plus AB plus AC plus ABC. Now little rearrangement of these elements, A plus B plus C plus AB, right, plus BC plus AC. Instead of AC we write CA plus ABC. And from here, you can see clearly that element wise, this element, A star B, A dot B dot C is exactly same as A dot B dot C, right? Because let's look at this now, right? So we have got A there, A over here, right? We have got B over there, B over here. We have got C over there, we have got C over there. We have got AB and AB. We have got BC and BC. We have got CA and CA. And finally, we have got ABC and ABC, right? Okay, so therefore, A dot B, that dot with C is equal to A dot B dot C. And this implies that A is associative. A satisfies, maybe that is a better way of writing it. A satisfies associativity. Okay, now let's now try to show whether this particular operation along with this set has a identity element or not, right? Okay, now that is the third property, right? So yes, so what is the so let us assume that E belongs to capital A is the identity element, right? So if A is an identity, and suppose we let that A is an element of capital A, then then A dot E will be equal to A, and which should in turn be equal to E dot A. Now A dot E is A plus E plus AE, right? And this is equal to A, which is equal to um, E plus A plus EA, correct? Okay, now let's like A plus E is same as E plus A, right? Because it's a rational addition, right? Of course, we'll prove things like this at a later stage in our problem. And AE, that is a product, is equal to EA. So basically, let's try to so these are rational products. So A is equal to E. So let us try to take the first part of this equation, right? We can equivalently take the second part as well, but without loss of generality, let's consider the first part of the equation. The first part of the equation, we get A plus E plus AE to be equal to A, right? All right. Now here the A and A on the left hand side and right hand side, they cancel each other. So we get E plus AE to be equal to 1. to be equal to 0, pardon me, yes, to be equal to 0. And we can consider e, and inside the bracket we can consider 1 plus a, right, to be equal to 0, right? Okay. Okay, so now what we do is that we see, the thing is that a can be an arbitrary number. So here we have got a product, right? So e is an element and 1 plus a is a is another element, right? So we have got a product over here. Now a can be any element, right? A can be any arbitrary element. But by the definition of small a being in capital A, the small a can never be equal to negative 1, which means that a plus 1 can never be equal to 0. So what we can get from here is that e should be equal to 0, and that is the identity, right? So e equal to 0 is the identity element. All right. Now that we have shown that there is an identity element, let's try to show that the inverse of a particular element exists as well. So let A belong to capital A, and suppose, suppose B belong to capital A is the inverse of A. Okay. So what will happen then? Then A dot B should be equal to E, and that should be equal to B dot E. Again, B dot A. I beg your pardon, this should be B dot A. Okay, so this implies that A plus B plus AB should be equal to 0, and that should be equal to B plus A plus BA. Correct? Okay. Now, without loss of generality, again, let us assume the first part of the equation, right? So the first part of the equation says that a plus b plus ab is equal to 0. From here, we can write, well, we'll just take the a on the other side, right? Because we need the value of b. So b plus ab is equal to negative a. And then let's see what we can do here. We can take b common, and we'll be left out with 1 plus a, and that should be equal to negative a, right? Now notice that a is not equal to negative 1, right? So a plus 1 is not equal to 0, so we can legally divide this entire equation by 1 plus a. So b multiplied by 1 plus a divided by 1 plus a is equal to negative a by 1 plus a, right? And we shall get from here that b is equal to negative a upon 1 plus a, and that, my friends, is the inverse. So for a belongs to capital A, the inverse is negative a divided by 1 plus a, which of course belongs to capital A. So this shows that these four properties show that uh, shows that there is a the set structure along with the operation is indeed a group. Now let's try to prove commutativity, right? So the commutativity is extremely simple. So in order to do that, let us assume that A and B are both elements of capital A. We'll find out A dot B, we'll find out B dot A, and show that both of them are equal. So A dot B is A plus B plus AB, and B dot A is B plus A plus AB. Correct? Okay. Now all these multiplications and additions are rational, right? So let's write this down over here, right? So in in the rational set, in the set of all rational elements, in the rational set Q, right? The addition of two numbers, the addition of two numbers is commutative. Okay, and the is multiplication of two numbers is also commu commutative. So addition is commutative. So let's take an example. So maybe P and Q. So P plus Q will be Q plus P, and multiplication, let's take the same numbers here. So PQ will be equal to QP, correct? So let's start with A dot B, right? A dot B is A plus B plus AB, and since A and B both belong to the rational numbers, so A plus B will be B plus A, and since BA, pardon me, I must have written this as BA over here, right? So okay, and AB can be written as BA. So this is equal to B plus A plus BA, and that is B dot A, right? Okay, so so since the natural operation of rational numbers is preserved in is somehow preserved in this particular set A, we can inherit the commutative property of the elements of the operations addition and multiplication to define that A plus B is equal to B plus A and AB is equal to BA, right? So since AB is equal to BA, therefore the so the dot operation is commutative over A, right? Okay, now since all of these conditions are satisfied, therefore we can say that A comma dot is an abelian group. Okay, so that finishes the proof, my dear friends. Thank you for watching.